Alright, example 3 and last example for this section. We want to find the surface area of z equals x squared plus y squared that lies above the circle with radius 1. So x squared plus y, z equals x squared plus y squared, if we sketch that, hopefully you guys remember, is, let's go ahead and change the color here, is something that looks like this. And we specifically only want to find the surface area above the circle with a radius of 1. So we know that this bowl thing, this keeps on getting bigger and bigger and bigger infinitely, but we only want to find the surface area that's associated with the space right there that's above that circle. So really what we're talking about, if we project this thing up, we're really only talking about finding the surface area of maybe this part of our bowl and everything below that red line. We're not talking about the rest of it, so we're just talking about what projects down here within that one area. So that's what we're looking at. So if we were to try and do this as the trivial parameterization, which we could certainly try, that would be x equals x, y equals y, and z would be x squared plus y squared. Well, that means that r sub x, well here let's write out r of x and y would be x, y, x squared plus y squared. So r sub x is going to be 1, 0, 2x. R sub y is going to be 0, 1, 2y. And then if I were to take the cross of those, r sub x cross r sub y, let's see, eliminating the I row and column is going to give me negative 2x. Eliminating the j row and column is going to give me 2y minus 0, but that now becomes negative 2y. And eliminating the j row and column is just going to give us 1 minus 0, which is 1. So what we would get for our magnitude of rx cross ry is the square root of 1 plus 4x squared plus 4y squared. That is going to be very difficult to figure out what the double integral of, because we're not going to have anything on the outside of that. What you would have to do is you would have to go and parameterize this thing again. So you'd have to parameterize it a second time. And I'll show you that that's still going to end up working out okay, but probably could have saved ourselves a little bit of work had we parameterized this thing using polar. So let's go ahead and go with polar, or cylindrical, I guess you would say. Whoops. Again, I'm trying to make a green eraser. It's not working very well. Let's make it go blue. Alright, so let's let x instead equal r cosine theta. Now remember that r here is varying. So because r is getting bigger and bigger as this gets larger and larger. Y is r sine theta. And z we have to put in terms of r's and thetas, but z is defined to be x squared plus y squared. So that's really going to be r squared sine squared plus r squared cosine squared. So that's just going to be r squared. I'm not writing all that out, but if you wrote it all out, factor out the r squared, you would see exactly that's what that gets. So then we're going to need to write out r of r and theta. Did not leave myself a lot of room, but I'll squeeze this in here, I think. So r cosine theta, r sine theta, r squared. So then we need r sub r, which is just going to be cosine theta, sine theta, 2r. Yeah. And then we need r sub theta, which is going to be negative r sine theta, r cosine theta, 0, because there's no theta in that last one. All right, now we need the cross product, RR cross R theta. So eliminating the I row and column, we're going to get 0 minus 2R squared cosine theta. So minus 2R squared cosine theta. The J row and column, we're going to get 0 minus minus, so that's plus, but it's going to end up being minus because we got to change the sign. So minus 2R squared sine theta. And then in the last one, eliminating the J row and column, we're going to get R cosine squared plus R sine squared, which again, if you factor out the R, is just going to end up being R because it'll be R times sine squared plus cosine squared. So then we're going to need to take the magnitude of that. All right, so we'll take the square root. Let's see, squaring the first one, we're going to get 4r to the fourth cosine squared theta plus 4r to the fourth sine squared theta plus r squared. This piece, once again, if you factor out the 4r squared, is going to give you 4r squared times cosine squared plus sine squared. So what we get after all that is the square root of 4r to the fourth plus r squared. And we can simplify that even a little bit further because I can factor an r squared out of that and then take the square root of that. So what we get is r times 4r squared plus 1. That's our magnitude. And then we have to take the double integral of that. So we'd have to integrate, let's see, r is going to go from 0 to 1. It says a circle of radius 1, so it's only going to go out as far as 1. Theta is going to go from 0 to 2 pi of r square root 4r squared plus 1 d theta dr. Could have written the 0 to 2 pi and then 0 to 1 backwards and then done r and then d theta. It doesn't really matter here in this case. Okay, we can split these, and we're going to. So 0 to 1 is r, so that's going to be r 4r squared plus 1 under the square root dr times the integral from 0 to 2 pi of d theta. Of course, we know that that's just going to end up being 2 pi. So that's going to be 2 pi. For this one, we're going to need to do a u substitution. And again, we need to show this process. So u is going to be 4r squared plus 1. Du will be 8r dr. So dr is du over 8r. I think I'm going to change the bounds on that one as we go as well. So changing the bounds, we're going to get, what is that, the integral from 1, plugging a 1 in, we get 5. Yeah, that looks right. Of r square root of u du over 8r, and then times 2 pi still from out here. R's are going to go away. I can pull the 1/8 into 2 pi out to the front, so we're going to get pi over 4 integral from 1 to 5 of u to the 1/2 du. Let's take the antiderivative. So now we'll get pi fourth times u to the 3/2 times 2/3 from 1 to 5. Simplifying that pi fourths times 2/3 is going to give us pi sixth. Plugging in 5 and plugging in 1, we're going to get 5 to the 3/2 minus 1. Okay, that is not a pretty answer, but that is the surface area of z equals x squared plus y squared that is only within the domain of the disk radius 1.